In this lesson, we're going to be covering independence, complements, and at least once probabilities. So as a reminder, first recall the OR probability formula, where if we're finding the probability of the union of events, we add the probabilities of the two events, and then we subtract out any overlap or any intersection probability that they may have. This is often referred to as the addition rule, since that is how you perform the calculation. We add. Okay, the idea of independent events, or what are independent events? These are events whose outcomes do not affect the probability of one another. So knowing that one event happened does not change the probability or the likelihood that the other event would happen. If E and F are in fact independent events, then we have a formula for their intersection. The probability of the intersection of two independent events is calculated by taking the probability of E times the probability of F. This is often referred to as the multiplication rule. But you have to be very careful. This is only true if the events are in fact independent. So a trap or a mistake that a lot of students and a lot of people in general make is that they apply this rule everywhere. But you have to be very careful. You have to make sure first you have independent events, and that is the only time when this applies. Okay, so first let's look at distinguishing between independent and dependent or not independent events. So it says determine whether the following events are independent. If I draw a card from a 52 card deck, I replace it, shuffle, and then I draw a second card. Would these two draws be independent of each other? In this case, yes, they would be. Because if I draw the card first, and then I replace it and shuffle and draw the second one, then what that means is what I drew the first time does not have any effect on what I'm going to draw the second time. So something like the first card drawn does not affect the second card drawn. I could even draw the same one. It would probably be pretty unlikely, but it could happen, right? So it doesn't matter. It doesn't, if those two draws don't affect each other. However, look at part B. It says, I draw a card from a 52 card deck, I keep it, shuffle, and draw a second card. Now are the two draws independent? No, they are not. Because whatever I draw on the first one is going to affect the probability of the second one. So the first draw does affect the second draw in this case. For instance, whatever I drew the first time, I have a 0% probability of drawing that the second time. It has changed the probability. There's no way I could draw it again. So it has changed all of the probabilities for that second draw. So those would be dependent, or for right now, just not independent. So if I get a question like part B, I cannot apply that multiplication rule. Okay, let's look at number 2. You are taking a multiple choice quiz. The quiz has 5 questions, and each question has 4 possible answers. What is the probability that you randomly guess and get? And part A says all 5 questions correct. So first of all, what's important here is the idea of randomly guessing. If you are just going through and randomly guessing on all 5 of these, you're not even reading them perhaps, you're just filling in bubbles, then these would be independent guesses. What you randomly guess on one is not going to affect what you randomly guess on another one. Those probabilities are not going to affect each other. So that's important to note, is that these are indeed independent events then. What would be the probability that you get all 5 questions correct? This would be like saying, what's the probability that I get the first correct and the second correct and the third correct and the fourth correct, and the fifth correct. So it is a very long and a very large intersection problem. Because they're independent, even though it's more than two, this applies to as many events as you can put together like this, then I know that I can multiply each of the individual probabilities together. So on any one of these questions, because there are 4 possible answers and only one of those 4 would be correct, there's a 1/4 probability of guessing any one of these questions correct. So the probability of the first one being correct is a 4th, times the probability of the second one being correct is a 4th, times, and we can just keep multiplying by a 4th for all 5 questions. So we basically are taking 1/4 to the 5th power. So I'm going to do that in the calculator. I'm going to take 1 divided by 4 to the 5th power. And that gives me an answer in scientific notation. So I need to move the decimal point over 4 places to the left. That would give me 0.000976562.5. Or if I want to look at this as a percentage, it is only a 0.098% probability that you're going to randomly guess all 5 of those questions correct. So next to nothing, basically, probability. Very slight. It's not 0, but it's almost 0 that you would guess all of those correct. What's the probability you would guess all 5 incorrect? Okay, so without writing it all out, remember, guessing that one incorrect would be the complement of guessing one correctly. So there is a 3/4 probability for each one of these, guessing them incorrectly. And since there are 5 of them in a row and they're all independent of each other, I can just take 3/4 times 3/4 times 3/4 times 3/4 times 3/4. So I'm taking 3/4 to the 5th power in this case. And that comes out as, let's say, 0.237. So there is actually a 23.7% probability that you will guess all of them wrong. What's the probability that you will guess 3 of them correct and 2 of them incorrect? Because that would be a 60% and technically passing. So what's the probability that you can at least guess your way through this with a passing 60% grade? Okay, so the 3 correct probabilities that are in a row are each a 1/4. So 1/4 times 1/4 times 1/4. And then the 2 incorrect ones would be a 3/4 and another 3/4. And again, they're all independent trials because what I guess on one does not affect what I guess on the other one. So let's see, what is 1/4 to the 5th power? Oh, whoops, sorry. Let me edit that to the 3rd power only because there's 3 of those. And then I'm going to multiply that by 3/4 squared. I can just do that in my head. That's 9/16. So it looks like that probability comes out as 0.008789, or about a 0.88, let's say, percent probability that you would at least pass. So even just passing is very, very unlikely. Less than a 1% probability of that happening if you're just randomly guessing. Suppose you're drawing from a standard deck. It says, suppose you make 2 separate draws. On the first draw, you get a king. You replace that card, shuffle, and draw a second time and get a queen. Find the probability of that event. Okay, so here, because you've replaced and shuffled, that tells us that it is indeed independent. So again, that's key. to decide that, then it means I can multiply the probability of these two events together. So what's the probability of getting, I'm going to call it king intersect queen. What's the probability of getting a king first and then a queen? I can take the probability of getting a king and multiply that by the probability of getting a queen. If we remember from our cards probabilities, there are 4 kings, so the probability of getting a king is 4 out of 52, which is the same thing as 1/13. And the same thing with the queens, there's 4 of those, so there's a 1/13 probability of drawing that as well. Multiplying those together, we get a 1 out of 169. And as a percentage, just because it's a little easier to understand that way, there is a 0.59% chance that that would happen. Suppose you draw 3 times in a row, each time replacing and shuffling before the next draw. What is the probability you would draw an ace all 3 times? Okay, so again, because of the replacing and shuffling, we're independent yet again. So what would be the probability of drawing an ace and another ace and another ace 3 times in a row? Well, there are also 1 over 13th probability for drawing an ace. So this would end up being 1 over 13 times 1 over 13 times 1 over 13, which is 1 over 2,197. And if we divide that out, that is about a 0.046% probability of drawing an ace 3 times in a row. So I would never want to make a bet of, I bet I can draw an ace 3 times in a row. This is very, very unlikely.